At this point in the series, you should have your robot characteristics picked out, such as the type of wheels you want to use, the gearboxes, and the overall size of your robot. I would highly recommend you watch all of the videos before diving into this step in designing your own drive system, as this section will be very technical. For reference, we have released our West Coast frame builder on GrabCAD using SolidWorks. If you do not have SolidWorks, you can use the viewer functionality on GrabCAD to get an idea of how these parts go together. We are going to use SolidWorks to create our frame so that the design can take shape and we cut out some metal and we get this robot built. I'm not going to go over all of the picks and clicks of SolidWorks because there are teams using Fusion 360, Inventor, Creo, and several other CAD programs out there that are free to FRC teams. I will, however, show any SolidWorks shortcuts that are used since SolidWorks is the most common in industry and FRC. Since I am a mentor and FRC alum myself, I don't like working on robots, so this video is going to serve as a guide for how I teach my current and future students how to do this step themselves using a tool I use every day as an engineer. YETI Robotics uses SolidWorks and SolidProfessor training software for the members of the team. If you want some additional information on the picks and clicks of SolidWorks, then I recommend getting a seat of SolidProfessor for your team. This also includes all CAD packages used in FRC, so there's training there for you. I would also encourage everyone to watch Adam Hurd's 973 ramp videos on YouTube as well, because he also covers FRC mechanisms, and these are a great resource for the FRC community. Thank you, Adam, for posting these. I'm going to post a link to Adam's videos, the 973 videos, in the description below. Adam covers picks and clicks well, but we're here to share our design insights on how we get our West Coast frame built using our specific method. Of course, you can use any modeling technique or software you want, but this is just our method, so you can copy it or you can do your own thing. To begin, I want to create a frame that automatically resizes given some adjustment, so we will begin the entire process this way. The drive rails and frame consist of 2x1 aluminum tubing with a 0.104 inch wall thickness. In SolidWorks, a 3D sketch can be used to create a layout for the frame perimeter. Using weldments, the 2x1 tubing can be placed on each line of the sketch, which creates the digital drive rails. Since your design is going to change a few times, I want to build some design intelligence into the model. I start by drawing a box and creating two variables for frame width and frame length. For now, I'm going to set these values to my maximum allowable perimeter size where my bumpers will eventually sit. When you do this in actuality, you might want to take off about ½ an inch for the max frame perimeter on each side, so the inspectors are going to pass your frame easier when you get to competition. This also gives you some tolerance with frame perimeter when designing mechanisms for the game. Using an extrude, I'm going to do the same for the height variable, which is equal to my tubing height of 2 inches since we're using that 2x1 tubing. This is going to be a dummy solid for when we create the frame, and the frame is going to be based on these parameters we just set up. The parts of our frame will actually be one SolidWorks part file. You can create individual drawings of each body later if you need to do that, but this is a very simple and efficient method of creating a frame assembly quickly. Next, I'm going to create a 3D sketch of the box as a skeleton. I'm going to hit my E key to turn on my edge filters, hit Ctrl A to select all the edges, and then I'm going to convert all my edges using Convert Entities to turn all of the edges of the solid into a skeleton sketch. Don't forget to turn off this filter if you use it, and you can also use the F5 key to toggle your filters up and down. Next, I will create two lines on the bottom to represent where our drive rails will sit and create a wheel well for the wheels. Something I want to note here is that I am creating an exposed wheel well instead of a protected wheel well. At this point in the design, your team needs to decide whether you want this or not. When you have an exposed wheel well, your wheel is going to strike an object before your frame, and this allows you to have a much lower frame and smaller wheels when you need to go over some large obstacles. A protected wheel well is easier to mount bumpers to, so your trade-off there is pretty simple. For most wheels, we set our frame rails back from the perimeter about 3 inches. Since you will have already selected the wheels that you're going to use, you're going to know if this is sufficient or not, or if you have other reasons to shrink your robot, you can do this now. I will turn my unused lines into construction geometry, save the sketch, and hide the dummy body using my Tab key. Just so you know, if you're going to do weight calculations using the software, you're going to want to use the delete body command on this body so your weight is accurate. Otherwise, you're going to have a giant slab of aluminum inside. At this point, we're going to add the aluminum drive rails and supportive framing for the robot. Setting up weldment libraries is something you will need to do no matter what CAD system you use, but I will put a link in the description for how to do that in SolidWorks if you've not been trained on this. I picked the same aluminum wall thickness for my 2x1 that VexPro sells because the VexPro aluminum is pre-drilled and makes placing the frame square during the construction a breeze. Since the extrusion has a hole every 1 inch, we will use this number later to square everything up. I am adding and locating my tubing based on the existing skeleton. Make sure to leave 3 inches between the perimeter and the wall of what is going to be the drive rail. At the end, I'm going to choose to trim this tubing to open up the wheel well so that we can go up ramps easier. If you leave this alone, this is what I consider a protected wheel well. Now, it is important to note that at this phase, we know how many wheels and what gearbox we're going to be using, so we can immediately start placing the parts. Placing the gearbox first is going to help you with the rest of the robot components. For this example, we're going to place our West Coast Products dual speed gearbox in the middle, but you can place it in the rear or the front of the robot to accommodate other designs. Since one set of the wheels is going to be on the gearbox driven directly, we will treat the whole pattern for the gearbox as the center for the first wheel. To get the whole diagram, we can pull the drawing from the gearbox source documents on the website and find out where the holes need to be. For our West Coast Products gearbox, there are 2 ways to mount it that YETI has used. For the less precise method, we have used the sliding bearing block method, but we typically use the inserted bearing flange method because it creates a nice anti-crush zone around the gearbox mounting location. This flange uses a 1.5 inch hole that you can cut with a hole saw or cone bit. The flange also uses 2 1/4 inch countersunk bolts to hold the flange in and screws directly into the tapped gearbox plates from your gearbox kit. Depending on what gearbox you have, this step is going to vary, and this is the time for you to figure out what to do. Either way, you need to place your mounting holes for the gearbox in the gearbox axle. We can draw out the hole for this component, which passes through the frame and into the gearbox with 2 screws. These 3 holes in this pattern need to be centered in the middle in my case, but at this stage I want to pause and talk about drop centering in more detail. The middle wheels of a West Coast drive must be dropped if you're not using any holonomic wheels. If you are using holonomic wheels on the corners, you can disregard this step about figuring out the drop center and just place the hole for the transmission at the exact same height as the other axles and the Versa bearing blocks. Now, in our experience, the most common drop center is 1/8 of an inch, but this number is super important to get right. If you have pneumatic wheels, you can adjust the drop to a larger number like 3/16, 1/4 of an inch, or even 5/16. But if you drop too far, your robot is going to tilt back and forth on the front and back wheels while the other set in the middle is on the ground, and this is going to make the robot harder to drive because it's going to wobble, especially on taller robots. This is one of those things that it does not hurt to do a little more research on Chief Delphi. You can read up on some of those drop center threads, but we have used mostly traction wheels or Coulsons, and so far 1/8 of an inch has worked for us every year on 6-inch and 4-inch wheels of different types. For 2018, we actually tried 1/8 of an inch on our 8-wheel drive 6-inch pneumatic wheels, and we scrubbed a fair amount. So we inflated the tires in the center more and deflated the outer tires a bit, and this small difference made an important impact on our turning performance. This was not as noticeable for us once we made this change, but in hindsight, a larger drop of 3/16 or 1/4 of an inch would have been better for our small pneumatic wheels. Once you go up to the 8-inch pneumatic wheels, the drop is probably going to need to be adjusted. The bearing blocks that you buy from Vex and West Coast Products have a 1/16 of an inch offset built in, where the center of the wheel sits away from the center that far away. It is easy to flip these upside down on accident, but there is a correct and incorrect way to flip them based on your design. We want our outer wheels to come up a 1/16 of an inch and our center wheels down a 1/16 of an inch for a total drop of 1/8 of an inch. At this stage, I'm going to go ahead and put in the 1.5 inch hole for the flange, as well as the 1/4 inch bolts that are going to bolt it to the gearbox through the piece of tubing. What I'll do is I'll tie all of these together so that I can move the drop center up and down. Since this is the center hole, we want to make sure that this stays exactly where it needs to relative to the schematic. On the schematic, these were about 1 7/8 inches apart, so I'm going to go ahead and dimension that as well. For this hole pattern on the gearbox, this is the center. So I'm going to make this about 15/16 from the bottom edge, and this will be the final location for my gearbox to mount. The reason I'm doing it this way is so that this number is the same for the top and bottom. You'll just reference the top or bottom edge depending on which direction you're going with that 1/16 of an inch difference. Note that for larger drops using the flange bearing block, you can really only move the flange, and the closer the flange gets to the inside wall of the tubing as it drops down, the more careful you need to be. It is possible to make the drivetrain without these particular bearing blocks, but we're trying to make it easy on teams and use off-the-shelf parts. And with a severe drop center, you may not be able to use these parts and you might have to make your own. Sticking with the intended design from Vex and West Coast products is something I recommend for your first West Coast drive. The sliding bearing block cannot do any other drop, it can only do one. And the flange bearing, I would recommend you don't go over about 3/16 for that drop. The outer holes for the gearbox are tricky if you're not paying attention. Do not drill a hole all the way through this tubing before verifying the screw size you're going to use to mount this, because we want the screw head to pass through the first wall thickness of the tubing and sit on the second wall, firmly holding the gearbox in place. Therefore, you need two different size holes. For a 1032 fastener, we use a .190 drilled through all, and then we bore the outside of the drive rail to a size like .388 that is large enough to let the bolt head pass through. This allows you to use the stock fastener from the gearbox kit without needing to buy fasteners an inch longer. If you mess this up, you can always insert a washer into the tube from the 1.5 inch flange hole, but man, that's a pain to do. I don't recommend doing that. That is the hardest part of the drive rails done. Now we just need to calculate wheel centers, which hopefully you have some idea from the last few videos. If not, we can use this model to verify the clearance around obstacles that we talked about in part 1 video. Since we're going to be using roller chain, we can calculate the center distances for a respective wheel distance and get a pretty close guess on how long a chain needs to be before it gets cut. This is a good practice, but not many teams actually do this. They just kind of grab the chain, cut it to size, and then they tension it afterwards. The best way we have found to compensate for this is to create holes for the axles that are oversized in the tubing. And then you can tension the chain with the VexPro cams and sliding bearing blocks that you can purchase when you order parts. On the SolidWorks side, all I'm really doing now is drawing a couple of construction circles that represent where my wheel diameters are going to be. I'm also showing you guys how I set my wheel center equations and wheel diameter equations up so that if I need to change anything later, I can. What you can do later is actually extrude these wheels and check later with the field elements and see if anything's going to hit the frame or if your frame is going to bottom out. At this point, I'm also going to go ahead and add my 1.5 inch holes. Since you most likely bought a hole saw or a cone bit that's 1.5 inches in diameter, I'm just going to go ahead and use this same universal size so you don't have to buy another tool. As long as this hole is approximately where the axle needs to go and you leave enough space around it, and you also consider the drop center, this diameter will be more than enough clearance so that you can still adjust and tighten the chain later. I'll simply add the holes to the center where I put the wheels. This is, after all, where the axle center is and where the clearance needs to be. After I add my two holes at 1.5 inches, I'm going to draw a center line from one end of the beam to the other directly in the center. And then at this point, I'm just going to make sure that my drop center is perfect. So my center drop should be a 1/16 down, and my outside wheels should be a 1/16 up for each of those for a total drop of 1/8 of an inch. I just want to make sure that we verify and get this correct at this point. Once we go ahead and extrude cut these, what we're going to do next is play with the wheel well. So I can change the equation for my wheel centers inside of my equations menu, and then I can check to see if my wheels are going to hit anything on the frame at this point. I never did take the ends off of my frame to open up the wheel well to make an exposed wheel well rather than a protected wheel well, so I'm going to use my trim command on my weldments menu to go ahead and take these little box ends off. Now, being this close to the end of the tube, the Versa block is not going to be able to reach because it's going to hit the tube and you're not going to be able to center the bearing and axle through the hole. So I'm going to go ahead and change that back to a different wheel center. Again, if you're using a chain calculator for this, you're going to know exactly where your wheel center needs to be I am mainly showing you guys the calculations so that you can make your design changes quickly and get to a finished chassis a lot faster. And later on down the road, if you're attaching other mechanisms to your robot, you come back and you find that, oh, this needs to move or this needs to change, it'll be a lot easier to do so. For teams with a mill, router, or laser cutter for tubing, this shape is what YETI uses. For teams without, we can just use a comb bit or hole saw for this part because it does not need to be as accurate as a gearbox hole does. This hole is simply a clearance for the axle to pass through the tubing. Now, I was creating this wheel distance from center using an equation, and I use an equation for drop as well. Sometimes we use in-context relations, but I recommend not doing that if you're new to this process and to SolidWorks. With this stage completed, we can move on to the assembly process and start dropping in our gearboxes. Go ahead and download the gearboxes you selected in Part 2 and save them as a part file so that the file is easy to manage and no parts fly around on you. If you've never created a West Coast drive, you should not be modifying your gearboxes, so this simplification of the part files will help you with your assembly process. Now, I recommend that teams do not have any parts in their top-level assembly. The way YETI creates our CAD, we have a top-level assembly that has a drive system and frame as one assembly. And we have a sub-assembly for everything else, like the electrical board, pneumatics, tower, climber, intake, all separate assemblies that make up the robot. At the top level, you should have maybe like 10 items. To make this structure, I can create a new sub-assembly called the drivetrain assembly with the frame we just made as the first part in this assembly. This is not the top level assembly, but this is the first assembly that will go into the top level when we are done, and then you can add towers, intakes, yada yada. With the drivetrain assembly, I'm going to focus on getting the gearboxes, wheels, bearing blocks, and chains sorted out right away. Drive system assembly frame first. Fixed, ready for gearboxes. Drop in one gearbox and we can build one side and then we'll mirror the other when we're done. Mounting the gearbox to check for hole alignment, everything looks good here. Now I can have my flange with bearing, taking note that we usually cut this axle down in the manufacturing process so that it doesn't stick outside of our frame perimeter. I recommend adding your number 25 or number 35 sprockets at this point. Number 25 chain takes an 80-pound tensile load max and is super light. Number 35 is heavier, but it can take 150 pounds of tensile load. Next, I'm going to put in my intended center wheel into the robot, along with some spacers if you feel that is necessary for your bill of materials. Lastly, you can modify the drive axle on CAD and put a screw cap in with the washer to complete the first wheel. This is going to hold the wheel onto the drive axle. Next, we will focus on the back of the robot. We want to let the back of the robot have inboard chain positioning because our design called for more space up front for components, so this is how we decided to do it. This axle for our Coulson wheels needed to be 4 3/4 of an inch long, but your axle length is going to vary depending on the wheel. Many teams use shaft collars, so we have included the length required to make that happen in this CAD file. After the 2018 season testing, YETI prefers to use Thunderhex with a tapped 1/4-20 hole, and a screw is capped and Loctited into the axle because for rough games we tend to rip shaft collars off and lose wheels. We tried this for an entire season on all of our robots, and we can safely say we will not be going back to shaft collars. You're going to add your wheel, bearing blocks, making sure you're careful about the orientation here, put bearings in the block, sprockets, and then we'll add the collars and hardware to the axle. Just a couple of tips on the assembly side. I'm actually using my width command to place a lot of this hardware on the drive rail, and then to figure out how far the components need to be placed from left to right, I am actually referencing the center hole of the gearbox drive shaft that's sticking out and that center wheel so that I get my center distance correct from my hardware and my chain distances. It is important at this phase to make sure the sprockets in the gearbox are aligned correctly, like so, and then the sprocket on this back axle is lined up with the inboard sprocket. Once you have that, we can make a chain in context, or you can make a separate part file that auto-sizes based on where the components are mated in case this changes. Note that you should make a chain for clearance detection later in your design and make sure that your spacing is correct and nothing is at an angle. Repeat for the other side, but this time we're using a shorter axle at 4.5 inches since this one is outboard and therefore shorter. One thing I like to do is take all of those components that I used just now besides the chain and create a sub-assembly for each. A back and front wheel assembly that includes all of the hardware. This allows me to create configurations for different axle lengths and wheel types for experimentation later if I need to change something. Once the whole side is done, mirror everything to the other side, making sure to create an opposite hand version of the gearbox if needed for asymmetrical gearboxes. Obviously, for an 8-wheel drive or 10-wheel drive, you have a little bit more work than the 6-wheel drive, but at this point you guys have already figured that out and you know what to do. The hardest thing here to do, guys, is the drop center. For an 8-wheel drive, the center is dropped on the 2 wheels. For a 10-wheel drive, the center is dropped once for the middle, and then the 4 wheels next to it have a smaller drop, followed by the outer wheels to make a smooth turning robot. If you want a no drop holonomic, flip the blocks upside down and just leave the middle dropped or raised the same height as the outside wheels. The next video, we will go over the belly pan and strengthening the chassis for construction to make this a seamless build. We'll also include some bumpers and talk about that a little bit. Make sure you watch all of the videos in the series so that you understand how all the parts go together and interact before you dive into this project.